I'd like to describe how a battery introduces a little bit of resistance into an electrical circuit. And I want to start by introducing you to Gustav Kirchhoff, and in particular to something known as Kirchhoff's loop rule. Now we're going to revisit Kirchhoff and both his loop rule and something known as the Kirchhoff's junction rule in our next unit of study. But the loop rule is important in our understanding of internal resistance of a battery. We can state the loop rule as something akin to the law of conservation of energy. So here we have a battery, a source of voltage or electric potential difference, and a resistor. And keep in mind, there's some amount of resistance in the wires, but we ignore it and just say all the resistance of the circuit can be treated as being located in the symbol here for the resistor. Well, Kirchhoff's loop rule says pick any point in a circuit. I'll pick this point on the lower left corner. Now it might be helpful for us to then create a frame of reference where we say electric potential is equal to 0 at that point. As we traverse around the circuit diagram in a loop, we should come back to this point of 0 electric potential. But as we trace our way around this clockwise loop, we go from a negative terminal to a positive terminal on this battery, and so there's a gain in electric potential across the battery. And as we go across the resistor, there's a loss of electric potential. The gain in potential and the loss in potential should cancel each other out. So we could say something like this, the voltage gain by the battery equals the voltage loss by the resistor. Or better yet, if we figure out the net change in electric potential around the whole circuit loop, that's got to come out to 0. So the voltage of the battery, let's use that symbol instead of delta V, we'll say V subscript B, the voltage of the battery has to equal, we'll call this the loss in voltage, we'll call the voltage drop across the resistor. So the voltage gained by the battery has to equal the voltage drop across the resistor. Now how do we find this voltage drop? Well, it just follows from Ohm's law. So the voltage drop across the resistor has to equal the current flowing through the resistor times the resistance of the resistor. That's just an expression of Ohm's law. Yeah. So the voltage of the battery is the same thing as the voltage across the resistor. Of course, if I say the positive terminal of the battery is point A and the negative terminal is point B, well, that means this side of the resistor is also the same electric potential as point A, and the other side of the resistor has the same electric potential as point B. So whether I hook a voltmeter up across the resistor or I hook a voltmeter up across the battery, in both cases it's just reading what we call VAB. So the voltage of the battery and the voltage drop across the resistor must be the same thing. Okay, pretty straightforward. If you've ever taken a battery out of an appliance that's been running for a while, if you hold that battery in your hand, you've probably noticed it's a little bit warm. See, the battery itself wastes electrical energy and converts it to thermal energy. And one way to say that is to say that the battery itself has some amount of internal resistance to it, right? So we'll symbolize that with lowercase r. Now there's the capital R for the external resistance of the circuit, which includes the appliance plus the connecting wires. In this previous case, we were discounting any amount of internal resistance. We treated it as if this battery is an ideal type of battery that doesn't get warm as it provides power to the external resistor. In that case, we're going to change the nomenclature yet again. Maybe instead of calling it V subscript B, we'll use this like script E. Now that stands for kind of an archaic term called EMF. Instead of calling it voltage back in the 1800s when the study of electricity was developing, what a battery provided wasn't so much stated as being a voltage or a source of potential difference. It was called an electromotive force. Which we just abbreviate to EMF, or just this symbol script E. And what you should think of for electromotive force is an ideal voltage. A power supply that has no internal resistance, that doesn't heat itself up as it powers an external appliance. Of course, ideal voltages are something like massless strings or frictionless surfaces or free lunches. They simply don't exist. So think of the battery like this. The battery is a combination of an ideal voltage combined with some internal resistance to it. Now, I'm not saying if you go and grab a hacksaw and cut open a battery, you're going to find a little resistor inside of it. That's not the idea. The concept is that the battery provides a perfect source of potential difference. However, it also heats up and wastes energy by driving a current not just through the appliance, but by driving a current through the battery itself. Okay, so what we want to find is some sort of relationship between, again, if we say this is the positive terminal of the battery and call that point A, and then this is the negative terminal of the battery and we call that point B, we'd like to know how does the voltage across the terminals of the battery compare to what we're calling the ideal voltage, or the EMF, of the battery. Well, I think you get the general idea. Since the EMF is an idealized voltage, it's greater than the actual voltage you measure across the terminal of the battery. So we could do an experiment to try to figure out both what's the internal resistance and what's the ideal voltage of any particular battery. I think we'd set up the experiment like this. Here are all the components we want. A voltmeter, an ammeter, a fixed resistor, a variable resistor, and a battery. So let's take the battery, connect it to our variable resistor, connect that in turn to the fixed resistor, and then use the meters to measure both the voltage across the battery and the current through the circuit. So let's see, we'll put the voltmeter over here so we can use it to measure the voltage across the terminals of the battery. We'll put the ammeter in line. So we'll just take a wire from the positive terminal of the battery and go into our variable resistor. Let me fix this up a little bit. Okay, there aren't really obvious inputs for this variable resistor, but anyway, we'll draw it just like this. Okay, we're just going to make one series loop out of almost all the components. I say almost all the components because the voltmeter is not included in this series loop. The voltmeter is connected in parallel across the terminals of the battery. And by the way, a voltmeter has a very large internal resistance to it. We'll say it's practically infinite. It's just the opposite for an ammeter. The internal resistance of an ammeter is practically zero. So by connecting an ammeter in series with the rest of the circuit, you aren't really effectively adding any more resistance, and therefore you're not changing the amount of current that flows in the circuit. Likewise, if the voltmeter was like an ammeter and had zero resistance, then this junction right here says current could flow to the intended part of the circuit, or the voltmeter itself represents a loop through which current could flow. Well, if the resistance of the voltmeter was practically zero, then all the current would take that path, and of course smoke would start to billow out of this voltmeter. In fact, it might even glow very briefly and be a short-lived light bulb in a way, right? So no, it's the exact opposite of that. Voltmeters have nearly infinite resistance, and therefore hardly any current at all flows through that loop of the circuit. Just enough current flows to make the voltmeter register a value, but the bulk of the current in the circuit is going to flow through this series loop that includes the variable resistor, the fixed resistance, the ammeter with practically zero resistance, and the battery, which we think of as being an ideal voltage combined with a little bit of internal resistance. So here's the idea. We're going to take the knob on the variable resistor and start with it at a high setting and turn the knob counterclockwise. So we're going to make the value of the variable resistor become less and less. Well, the effect should be that the current that flows in this loop then should increase with less overall resistance. If you want, we can say that the fixed resistor and the variable resistor, because they're in series, just have an effective overall load resistance that's just equal to the variable resistor plus the fixed resistor, right? So by decreasing the variable resistance, we're decreasing the load resistance, which increases the current in this loop, but the battery itself is part of that loop. So we're increasing the very current that flows through the internal resistance of the battery. All right. Maybe it's better we diagram this. So instead of calling this V, we're calling this EMF, internal resistance. And then if we picture a battery, then from the positive terminal to the negative terminal across there is V subscript T, the voltage across the terminals of the battery, the terminal voltage. Here's our R variable and the R fixed. Now, I guess what we're saying is we're going to put an ammeter in that series loop, and we're going to connect a voltmeter in parallel with the terminals of the battery. Well, here's what we'll find. When this variable resistance is at its maximum value, then the voltage across the terminals is as great as it gets. Maybe we get a data point here. Now, as this variable resistance becomes less and less, it's no longer the maximum value, it's some intermediate value, then that means the current flowing through the circuit becomes a little bit greater, right? If the resistance goes from its maximum value to something slightly less, with less current, with less resistance in this load, we get greater current flow. So current is on our x-axis, So the current gets a little bit greater, but the voltage across the terminals of the battery gets a little bit less. So we get maybe this data point right here. And then we change the resistance of our variable resistor to its minimum setting. That means the resistance of our total load becomes as small as it gets, and so this current becomes as great as it gets, so even a larger value of current that's graphed along the x-axis, and that leads to the least amount of voltage across the terminals of the battery. Well, all these data points form a line, and if we make a line of best fit through every data point, and there are a couple key features of this graph. First of all, the intersection of this graph with the y-axis represents the maximum voltage. What that really happens to be is the EMF of the battery. The slope of this graph is equal to the negative of the internal resistance. In fact, there's an equation that says the EMF of the battery, its ideal voltage, is simply equal, well, yeah, we can write it like this, to the voltage across the terminals plus the current multiplied by the internal resistance. Now, that's consistent with Kirchhoff's loop rule. Let's go back to this diagram and pick any point we want to. Let's pick this point here. Now, that's a point we couldn't actually access with a wire because it's internal to the battery. But as far as looking at the circuit diagram, we're welcome to analyze that point. So as we work our way around the loop, we can say there is a gain in electric potential equal to the idealized voltage of the battery. We continue on until we get to our next circuit element. And we'll treat these two as being together as one, right? And we'll just say that the resistance of the load is this quantity, capital R. So now there's a loss in electric potential. And by Ohm's law, that's just equal to whatever the current happens to be multiplied by the total resistance of the load. All right, we continue through the circuit, and we get to our last circuit element, which is the internal resistance. So again, according to both Ohm's law and Kirchhoff's loop rule, there's a loss of voltage across the resistor equal to the current multiplied by the internal resistance. Okay, well, we could also think of it like this. We can say we're kind of blind to what's internal to the battery. All we know is it has some terminal voltage to it. So again, if we apply Kirchhoff's loop rule and we pick this as the point that we start at and finish at, then the first thing we encounter, we go across the battery. So we gain a potential difference that represents the voltage across the terminals of the battery. The next thing we get to in our circuit is the combined load, which is the variable resistor and the fixed resistor. So minus I times R load. And then we're back to where we started. And so we can say that equals 0. Oh, by the way, I've left off the equals 0 in our first case. So in other words, the terminal voltage is I times R load. So I can substitute that here. So EMF minus terminal voltage minus I times internal resistance equals 0. And so you see that this is consistent with the equation we just stated earlier that describes this graph. Another way to say it is that the voltage across the terminals of a battery is equal to the ideal voltage minus the internal voltage drop due to the internal resistance. And in fact, That's probably the best way to say it if we want to describe the shape of this graph. Or maybe I'll say it just a little bit differently. Say V terminal is equal to negative Ri plus EMF. Now this looks like Y equals mx plus B. What did we graph on the x-axis? The current. What's the y-intercept? The ideal voltage. What's the slope of the graph? The negative of the internal resistance. All right. Now this is a head scratcher for some folks. Some people see this graph and say, wait a minute, having a negative slope seems kind of funny. After all, I thought Ohm's law tells us that voltage is equal to I times R. So we can write V equals IR, or we can say V equals R times I plus 0. So if we put voltage on a y-axis and current on the x-axis, then we should have a y-intercept of 0 and a slope equal to positive the resistance. In other words, we expect to get a graph like this, where the slope is equal to R. Well, yeah, that's exactly the graph we would get if we were trying to graph the voltage across the resistor. But that's not what we were doing in this experiment. Notice our voltmeter was connected across the terminals of the battery. So this graph with the negative slope is describing the terminal velocity of a battery, which is always less than its idealized voltage by an amount equal to the internal voltage drop due to the internal resistance of the battery. Thanks for watching.